So here, guys, we are going to look at the ForkJoin framework of ForkJoin pool, how it works. So we already mentioned that the ForkJoin, think of it like divide and conquer, where you have work that you want to distribute amongst threads that are available in the pool. So I'm going to start with the demo to show you that when you say ForkJoin pool equals to new ForkJoin pool, what this does, that it creates a number of threads equal to the number of processors or core. So if we look at this, you see what this method is doing. Get runtime available processors. That's the number of threads that you get by default when you create a ForkJoin pool like this. And then you have work that you want to apply the divide and conquer rule on, and then you take that work, you pass it to the thread pool. When you say invoke, you are telling the thread pool, execute this task, perform an action on this particular task. So there are ways in which you can work on your thread pool implementation. No, not implementation. You can utilize the thread pool. You have what we call a recursive action. You have what we call recursive task. So let's look at the recursive action. So recursive action, I'm just going to go to the Java doc and we read what it says. It says a recursive resultless ForkJoin task. This class establishes conventions to parameterize resultless actions as void ForkJoin task, because null is the only valid value of the type void. Methods such as join always return null upon completion. So you can think of it as void. You see that it's a ForkJoin task that has a void type, and a void type, we saw it is an uninstantiable placeholder class. References the class object representing a Java keyword void. It means nothing. Recursive action, we see that it extends ForkJoin task, but we void. Let's see this one, recursive task. You see it extends ForkJoin task with some type, which can be anything. So that is fine for now. So what does this recursive action does? So we see that we have a list of numbers here that we want to sum up, or we want to perform some action on that particular list of numbers. So here we just want to display those numbers. That's it. And then we see that in our compute method, our condition says if the list contains less than 2 or less numbers or elements, perform this operation. Else, you're going to divide that list and distribute it amongst different threads. Basically, you're dividing and conquering. And at the end of the day, if we run this code, I'm just going to come here with the recursive demo. We have this list. You can have many. Let me say, for now, let me just say list dot stream dot range that generate one. Okay, I want okay, let me say int stream dot range So 0 to maybe how many? You can just say 1000. We want 1000. Then we have to box this and collect it. Then we have numbers like this. So as you can see here, we have 1 to 1000 numbers, and we are passing this list to the pool, and we want to print it. You can think of this as some tasks, and then what we do is that our implementation will divide the work amongst threads to be done by the work. So let's just run this code and see what happens. See that we have all this work and we don't even have them printed in the order they are appearing. We see here it comes. It's because they are given to different threads, and each thread will do its own work. So as we can see here, we'll have thread printing 40 and 41, 100 and 101, just like that. So if we want to print them in the groups of maybe 5s, we'll have to put 5 here. Then we run it again. We see that 901, 902, 903, 15, 16, 17, 18. It's just that when the division happens, okay, we see 3, 4, 5, 6, 7, 8, 9, and all that. That's fine. We can look at that later. Let's just leave it like that for now. But the basic understanding should be that you are dividing this work. Let's go back to 2. You are dividing this work. You see what we are doing. Say if the list contains less, what do? We come here, we divide the list into 2 groups, this one and this one. Then we create another task, then we invoke. So this invoke will eventually call this method again recursively. This is why we call a recursive action. So it comes again with the list that has changed, then it does whatever it needs, and then at the end of the day, since this method is void, doesn't return anything. So that's it with regard to the recursive action method. We see that this interface, recursive action, contains compute method, which is abstract. Then we override that method, we provide the implementation. So what we are doing here, we are doing dividing of work amongst threads. Just that this invoke all is hiding some details away from us. There is something we will see. Let's go to the recursive task so that we can see now. We don't use the invoke all. See what we do here. So we have this and we're returning an integer. So let's see what we are doing here. So with this one, we are summing up the numbers. So recursive task demo, what I'm going to do, I'll just copy this as well and put it here. This is the list that we are passing, 1 to 1000, that we want to perform addition on. Because remember, recursive task allows you to return something. So what we want to do is we want to perform some addition. So we can just put 5 here. So we are saying if the list contains less or equals to 5, add those numbers and return the result. If not, divide the list into 2, create sublist, then create 2 of this, and then what we are doing here, we are performing a fork. So when you do this, it's like you're saying create a separate thread for this to work on this. And remember that we are still on the current thread. We create separate threads and then we wait for them to complete, then we return the result. And since this is happening recursively, you will have a thread you will fork this particular thread, which means that this will create a thread, and that thread would try to execute the compute method, and it will not block this particular thread. This one will be created again, and it will try to execute the compute method. And then when they are done, for each one of them, you will call the join. So this is going to have some recaching attached to it, and when they are done, they will combine the results together and send them back to you. There is something you have to know with join. Join blocks. That means when you say t1.join, you will block. This will wait for this to finish before it can execute this. So let me just run the demo for it. So this is the summation of those numbers as we see. So then we have another form of recursive task that I want to show you before I complete this tutorial. With the previous one, we saw that we fork, we join. But with this particular one, what we are doing is we just fork one, which is task 2. And then we just call compute on this particular one directly. So the question is, why can't we put join on before the compute? So if we say t2.join plus t1.compute, this will not be efficient because join blocks the current thread, which means t1.compute will also not be executed in parallel with the current thread. But when we return t1.compute plus t2.join, allows t1 to compute to use the current thread without waiting, which allows t1 to execute in parallel with the current thread. So you can also use this one to do the computation that we want. So let's just run this code. So you see that, guys, we get the same results, but we have actually introduced compute. Here we are using join, and we get the same result. So guys, this is all about the ForkJoin. My advice is you can just play around with it and explore it to see what you can be able to achieve. Thank you.